A quick note before we start, I selected the wrong microphone, and so my audio sounds like crap. Our guest sounds great. He's talking about some really interesting stuff, so I hope you stick with it. I promise to do better in the future, and my apologies. This is the Amp Hour Podcast, released November 29th, 2020. Episode 519. Simulating Embedded Hardware with Michael Gielda.
Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hi, I'm Michael Gielda. I'm VP Business Development of Antmicro, and I'm also Chair of Marketing of Chips Alliance, as well as Vice Chair of Marketing of RISC-V International.
So that's a couple things there, Michael. You've got your work cut out for you.
Yes, although I must say all these things are related. It's very easy to wear those hats because if you believe in the mission of the orgs you represent and they're convergent, then you're kind of doing several things at the same time, but it's not a problem.
Yeah, and I think I started hearing about Antmicro when I started hearing about RISC-V, and then of course I heard it from Tim Ansel over and over and over again because he speaks very, very highly of you, and he introduced us, and I appreciate that from Tim. So could you tell us what is the connection between Antmicro and RISC-V?
Yeah, the connection runs many years. Actually, we're one of the original founding members of the organization. It all dates back to a workshop at CERN where, we went and met the original RISC-V guys, the people from Berkeley and Sci-5.
Mm-hmm.
And since it actually dates back to probably 2010 when, we started dabbling in open hardware in general. We were early adopters of, OpenRISC, probably one of the few companies that actually kind of did some business with, OpenRISC, the niche thing that it was. And we always believed that hardware has to go along the same route of software, just being open source, being more collaborative. So we had been early adopters of these kind of open hardware related things. But for a long while, it felt very lonely, right? You couldn't really get any serious business going.
Right. Hey guys, how about we all build our own chips? What if we just all go to the fabs and build a completely open ISA? That would be great. And crickets.
It sounded fairly crazy pre-2014, 15. Yeah, exactly. You sounded like you were the only person that wanted that. So it all changed there at CERN, and somewhere around the middle of this decade, RISC-V was formed, and we got on board like extremely early alongside Google and a couple of others, and since then it's just been a constant story of working with open hardware. It's not to say that we only work with RISC-V, right? Actually, we're also a member of Open Power, right? But which kind of is also really great to have been open sourced last year as an ISA. But we also do ARM development. We're very agnostic to technology. It's just that we have obviously a strict preference for open source, and here is the convergence point of RISC-V, which is an open ISA, and it also kind of brings together an entire community of people that care about this kind of thing.
Right. Okay, so you guys work with a lot of chipsets, and people are listening now are like, okay, but what do they do? And so can you tell us about Renode and then kind of how Antmicro kind of fits into that whole ecosystem then?
Sure. So Renode is one of the tools that we build because we believe when you do something, you also have to think about the workflows, about the tools, how are you doing things, whether you're just copy pasting what other people did or you're kind of inventing new ways. So on the ground level, we are actually a service organization. We build things for people that need them. But having said that, we just don't do anything. We will provide engineering services that are based on open source, and preferably they are open source engineering services. So whatever we do gets open sourced. Renode is a tool that we build for ourselves. So even though we do services, we have a lot of R&D internally as well that kind of feeds that kind of service organization. And Renode is one of the earliest tools we built. It's been around since 2010 in some form. It's a simulator, of course, open source, that allows you to just build embedded systems faster, since a lot of our work is in embedded systems, or as some other people call it, edge AI systems. Renode helps you to kind of build out those systems quicker because it allows you to simulate them without the hardware, which just makes you able to work on your computer and possibly put this development in a CI context, on a server, execute tests, gather metrics without touching hardware.
Yeah, this seems like it seems like if I had to simulate, or if I had to assimilate what, or that's not even the right word either, but basically if I had to say what Antmicro does, is basically you guys are the pure distillation of software coming to hardware, it feels like, because a lot of the things you're saying there, like CI, which is continuous integration, and all these simulations, I mean, it really allows you to bring software methodologies into the hardware world, whereas, there was pieces there before, there's always been scripting and similar things in there, but not maybe at the same level and the same confidence level that people would build entire systems and simulate entire systems and work all the way through to an end goal. Is that a fair assumption?
Absolutely. I mean, I think you summarized it really, really well. We always say we're a software-oriented company that's working with hardware. So even when we build hardware, we always try to make sure that we do it in a software way. Our engineers that are like nominally, hardware/electrical engineers, they also have to know how to program. We kind of try to think how we can avoid all those proprietary and uncollaborative ways of building things and instead transition to as script oriented and CI driven flows as we can. There's a lot of difficulties in doing so, but it's a worthwhile thing to try to think about these difficulties and how they can be worked around.
Right. And so when someone's using Renode and they're like the page talks about like assembling a system. Is it basically like you're building the actual chipset and all the peripherals on board? So like say I have like an STM32F403 or something like that. I only care about certain peripherals on that. So I care about the core, the Cortex M4. I care about the SPI peripheral, something like that. And am I piecing that together, or like what is the actual implementation then when people are building up these simulations for their use cases?
So how Renode works is it observes the world which is built from blocks. Like every IP vendor, every kind of silicon manufacturer, actually, and board manufacturer, right? They'll take some components that pre-exist. Very, very rarely will they actually build something from scratch. They'll take some components, put them together, and that's what you see in the end. That's what you program against. That's what you build. A board like the STM32, F4 or something, will have obviously the STM chip on it, but it'll also have a bunch of peripherals externally, potentially like some sensors and I/O and so on. Even inside the chip, it's still a modular design. So, like the entire portfolio of STM's microcontrollers, they will have families that share quite a lot of internal building blocks perhaps in different configurations. If you observe how these things are built from abstraction levels of complexity, but on all of those levels you have clear building blocks, you start to realize that a lot of the work is not just in like implementing what's needed, but also putting together those abstractions in a clever way to save yourself redundancy and work that's not really needed. So how Renode works is it tries to capture that kind of those abstractions in interfaces and classes and models that can be reused and reconfigured. So if you want to build like a virtual STM32 board, practically you put together a bunch of things in a config file instead of like writing code. And I think that's a very important psychological change, as well as it has implications that go very deep, because theoretically, of course, you could write all of these things in code and compile them. It would work. But at the end of the day, if you're really after just like modeling a system and running your software, you don't really want to be compiling your simulator, right? You want to get your simulator and just use it as a tool. So it's a tool that clearly separates the development perspective of the tool itself with the user perspective, and the user, of course, probably is a technical person, but they don't necessarily need to understand how Renode works internally to use it.
Yeah, I feel like, especially coming in from the hardware side, I'd love to have like from a confidence perspective as well, like as long as these different blocks have been vetted and, there's confidence in the system, which I'm sure there is, I'd love to be able to just, pull in and just say, hey, here's a SPI block, here's an external sensor, here's the core. I'm probably will just forego the entire process because of that complexity. And this seems like it kind of fast forwards and allows people to access it easier as well.
Yeah, absolutely. I mean, we have right now cases where like one of the local universities is using Renode for, kind of just classes, right? And we're also kind of building a module for an edX course that's already has 6,000 people signed up, where you want to put Renode in front of them and have them develop for Renode, and you don't want them to have the feeling of, oh, this is harder than my dev board, right? You
Yeah,
want the
yeah,
opposite. You want them to be like, this is exactly the kind of software oriented experience that I know from other types of development, right? Like if people are
right.
into web design or they're into developing some kind of command line software and so on, like it's just so easy to get started. You grab a project from GitHub and you can start hacking in 5 minutes. With hardware, it's like you order your board, you open up like some a manual, you
Install the tool chain.
hook it all up, download tool chains, so many things. We can't avoid everything. Like you still need the tool chain to compile a binary, right?
Sure. Yeah, right, right, right.
but like well, okay, actually we have demos, we have precompiled binary demos that we also ship, because we just saw if your first 5 minutes experience is, oh, just go compile your own binary and then you can run Renode, a lot of people get discouraged. But if you tell them, look, here's a precompiled thing, you can run it in 3 minutes.
Yeah, start with this, get the dopamine flowing, and then eventually you'll come back and try it again with your own customization.
Yep.
Yeah, that's really great from it's interesting you mentioned the educational aspect too, because one thing in COVID era of like, people being a lot more remote and really just generally thinking about remote, maybe even outside of education, the ability to access what you think is hardware, right? Or what looks like, a set of IO or looks like a set of registers. From the software perspective, it's not that big a difference, but it can have a lot of logistical implications, right? So if you're running a class of 6,000, like you mentioned, now you don't have to ship out 6,000 boards. You have to worry about shortages, which is another problem that's happening in the supply chain right now. It's just like you just ship bits instead of atoms, and that's really great for making things more widely available.
Yeah, absolutely. I mean, look at what Docker did for development, for example. We've been called the
Mm-hmm.
Docker of embedded, which I like.
Oh,
It's
interesting.
not precise, right? But it's kind of a cool, catchy phrase.
Yeah, and I feel like that's the software people love it too. So it's like, yeah. Can you explain what Docker is for the hardware folks out there that don't know what it is?
I probably think most people do, but yeah, Docker is a containerization framework that just allows you to run software anywhere, because you package it up
Mm-hmm.
into a container that runs on top of your operating system, but it's an isolated thing. It's both isolated,
Yeah.
that's the one good thing, and it's also kind of reproducible top to bottom, right? So kind of you're not worried that whatever you're running, another person's going to be running the same thing but getting something a little bit wrong. Kind of what you have with dev boards and someone connecting a wire differently.
Yeah, I kind of think about like VirtualBox or something like that as well, right? It's like a shrunk down version of VirtualBox without running an entire OS. You're running just the portions that you need inside this thing, and then you have the inputs outputs. So you might be able to access like a IP, like the Ethernet element of it, and be able to push packets in and out of it. But yeah, it's like a much shrunk down version of a whole system.
Yeah. So getting back to the logistics, I mean, what containers
Mm-hmm.
did for many domains of human activity was to just simplify collaboration and reproducibility and scalability of things, right?
Mm-hmm.
That's really an inflection point where things started scaling very rapidly, and people started doing things like continuous integration. Partly because it's not that continuous integration wasn't possible before,
Mm-hmm.
but it's just gotten so easy with containers and things like this. So I guess it's the same with simulation. It's not that these concepts are new. It's more like once they get past a certain point where things are just easy to do, more and more people start to do it. So the logistics aspect is, I think, actually one of the most important ones. It's not
Mm-hmm.
about, you know, we have engineers that come to us and say, oh, I've been doing simulation for years, so how's your thing better? And we're like, well, if you have been doing simulation for years, that's great. You're probably going to find Renode very useful, but it's
Mm-hmm.
not that this will necessarily change your life. It's going to change the life of the people that didn't use simulation before. We're trying to make it easy
Yeah.
enough for them to transition from like 0 to 1. And we see that the group of people that are effectively using simulation in day-to-day development is very, very small, as
Mm-hmm.
compared to, everyone should be doing it, right? There's no reason why you shouldn't try to put your development into a computer, because if you put it in a computer, it starts being scalable, it starts being reproducible. You can just, if Renode, you can just take a snapshot of your work and just send it to a colleague, and they're going to run it, and they're going to have like binary, the same thing that you're running without any possibility of difference. Whereas, of course, if you try to do the same with like a physical set of hardware on your desk, you're going to get something wrong anyway. And besides the time it takes to ship someone an actual hardware kit or a set of hardware kits, it's just, it doesn't happen. In reality, we always say testing in embedded systems, like in most places, it doesn't really exist. Like, people avoid testing if they can.
Well, because then it's all field testing at that point, right? It has to be in the physical realm usually, and then there's a ton of overhead that's associated with that.
You shift testing to your users. That's what people do. And
right.
We know that because we have customers, right? Like, we have customers that come to us to build very serious, industrial embedded products, right? And most of the time, testing is not really on their mind. We have to like remind them of the fact that, hey guys, testing is a great idea.
Yeah. Okay, so I am one that does not test, at least in the. So I have this new project that I've been working on that I talk about a lot. It's like it's got an NRF52 on it, and it's got a cell modem, and it's got a bunch of peripherals and stuff like that. Is that something that would be a good use case that we could kind of use as an example here?
Absolutely. I mean, we're actually adding a NRF-based platform right now for like Google's Tensorflow Lite team that we're working with, and kind of reworking their CI to be automated with Renode.
Got it.
And also the Harvard course, that's actually the platform they're using. So it's a great example.
Okay, so right now, here's actually a good example. So I have a firmware developer. He logs from far away. He logs into a laptop that's sitting on my bench. The laptop sitting on my bench is using a J-Link to program the board. It's got a serial terminal coming off of it that goes back into USB to serial to that laptop, so that he can quote unquote see everything. There's USB. There's a webcam that was very, very proud of setting up this whole thing. But it sounds like all this stuff would be kind of obviated by the idea that, like, if it's just sitting as a known simulation target, he could not do that anymore. Is that right?
Exactly. Yeah. And you know what? If he actually did this, that's exactly what I'm talking about when I say we have people coming over and saying, oh, I already like set up this extremely complicated mechanical rig that can test things.
Right. Yeah. Physical realm. Right. I mean,
like, great. Like, it's very good you did this, because like if you don't have simulation, you should do that. You should test your things. And once you do that, your incentive to do simulation kind of decreases a little bit. I still think that people should do simulation, but like, I'm talking about the people that didn't have the opportunity to set up this 100-unit, rig in their server room. And with COVID and with distribution of work that you have to do, suddenly, like, even accessing this kind of infrastructure, even if you have it, right, it becomes so difficult sometimes that people turn to us and say, okay, I've tried physical, but like, we need to simulate.
I can give you a great example. So yesterday, Bilal was like, hey, can you check and see if the SPI signals are actually firing on this board? And it's like, okay, so now I have to like check that, and I'm happy to do that, of course. But he's then dependent on the remote person being near the hardware. And if you have 100 units set up in your server room, you either have to somehow tell that the LEDs are blinking or that the signals are going properly, whatever. Whereas I imagine in a simulation, you just see the signals going or not.
Yep. It's exactly, the physical realm is very indirect, right? So you only see that something's happening because you're looking at the LED blink. Now, whether the LED's actually blinking when the things happen, how do you know, right? Like, sure, you're relying on your software being correct, but perhaps it isn't. That's what you're testing. So the thing you're testing is kind of influencing your testing procedure itself, and things get hard.
Yeah. So how would then, okay, so then we're going to replace this janky hardware setup I have, and we're going to create a simulation of the board. How then, so, Bilal's writing firmware, he's making a binary that he is then loading onto this physical hardware. What does it look like then when it gets loaded into a simulation in this case? Like, what are the mechanics of doing that sort of thing?
I mean, you just have to turn on Renode. You have to instantiate the platform, which, assuming that there is a script that describes that platform, it's a one-line command. And of course, inside that script, there's a bunch of things, because we're, setting up this platform and potentially doing a bunch of things. But after that, you just load the binary and you start.
Okay.
So it's 3 lines of scripting that gets you there.
That's a lot of work, man. Oh, geez. Versus like having a webcam. I mean, it's so easy. Okay. Okay. So you load it in though, and then what is the actual like? What do you see? Is there like visualization? Is there like plotting? Like what, or is it all kind of configurable in that you can kind of quote unquote see whatever you want there?
Excellent question. So basically, we try to integrate with external tools for doing things that those tools do well, right? Like, I mean, we're always tempted to create our own tools for everything. We're engineers after all. But
Sure. Yeah.
in reality, of course, you don't really want to redo the work of many brilliant people. It's not that we necessarily need to reinvent the wheel. In many places, the analyzers, as we call them, already exist. A good example is Wireshark, where, yeah, we could write our own packet analyzer that analyzes, IP packets and so on. But actually, people have already done that, right? What you
Yeah.
need to do is hook up to those tools and provide them with the data that they need. And so we have one specific thing that we wrote that we think is very useful, and we just didn't see another way of having it easily, which is, given the fact that we're a simulator, we can actually produce trace data. So the execution of a specific binary, right? If you just let it run, what's going to happen is instructions going to get translated and executed, and then it's going to access some memory addresses and peripherals and stuff like that, right? This is great data that you can actually get from Renode interactively. Of course, you can always you can stop and read that data. You don't even have to stop, right? You can read that data online while things are running. But like one thing we did recently, and that's the Renode 1.11 release, includes what we call metrics analysis, which is we can extract this data from the runtime, and then we take that trace, we can put it in whatever, like we can analyze in a Jupyter notebook if we want, right? And produce graphs of like executed instructions and what cores are working at various times of the execution. So you could, of course, see that perhaps your cores are not really under very heavy load. You're thinking that you have a multi-core code until you actually look at whether the code's multi-core. And I mean, these things are not completely unfeasible with hardware because there are like tracing units inside cores and stuff like that. But in Renode, you don't actually have to code anything or include any kind of instrumentation in your code because it's the simulator that's pretending to be your hardware, right? And since we're pretending to be the hardware, we have all the information about what the software is trying to do to the hardware. We can essentially store this trace information as abundantly as we want.
Right. Yeah. No memory limits. I mean, or really the limits of the system, which is much more massive than an embedded system might have, or even maybe an external probe might have. So.
Yeah. So I mean, Renode is a CLI-based tool mostly that has a very good API, and then we are of course working on a lot of different crazy ideas. And for example, this relationship with Google, the thing that we're building in terms of TensorFlow Lite and metrics stuff, and generally measuring how well ML code executes on small embedded platforms. I think this will generate a lot of dedicated tooling as well, right? But in areas where the tooling exists, like network analysis, it just doesn't make sense to try to do it yourself. You just have to figure out the formats that people use, and then you just generate the data in a format that can be then analyzed with further tools.
Okay. So then you mentioned that you can also simulate like external sensors. So I'm going to give an example of a sensor that I have. So I have like a LIS D8 D2 sensor. It's like an accelerometer on board, right? That's one of the sensors I have. What does that look like when that's actually configured in the system as well? Or is that configured in the system? What does it take to push something like that into a system like this?
We have a bunch of accelerometers modeled. So basically just added to a config file, we have what is called a REPL files, the Renode platform files, hence REPL. And because we have REPL, RESC, and the RE prefix, and then the actual name, the format. So in the REPL file, you'll find probably a sensor hooked up somewhere, or if you want to hook it up, you just add it. You can also add it online. Of course, you can always add it from the CLI in runtime as well. Yeah. But like, of course, normally you'll do it in a script. And then if you have the accelerometer hooked up to your, whatever it is, I2C, whatever is the interface of that sensor, then you'll just have a virtual accelerometer to which you can potentially, for example, feed data from a file, right? And that's again a command,
Yep.
like feed data from file. You give a file name, and then those data points will just be fed into Renode, and the software will assume that that's the readout they're getting, right?
Right. Yep. Yeah, I guess that's the thing. What I'm wondering about is like, okay, so now thinking about moving things towards testing and what you want to actually test on a test stand. So, you might want to push in. So to move outside my example, but you might say you're making like a quadcopter controller or something like that. You might, for some reason, want to actually test some function of the, maybe you're having motor controllers that you want to drive in certain ways, but you want to simulate the accelerometer that is causing that motor controller to do this thing in response. You would need some way to actually stimulate the system so that you could then measure the system. And I assume then you could even, measure the output of a motor driver as well. And so it just comes down to I just think about then everything becomes a test vector, right?
Yeah, exactly. And actually you have to be a little bit clever about these things, because once you move to simulation, you realize, okay, I can now do testing that doesn't make testing easy, right?
What do you mean by that?
So if you want to test whether something's actually working, how do you do that? If you don't have an opportunity to do that because it's just hard, you just ignore the problem and your conscience is free, right?
Got it.
But if you actually have the possibility to test things properly, you realize, okay, testing is a thing in itself. It needs very clever thinking. So we have the ability to feed data from files. Now, how many files should you have? How many scenarios should you test?
Right. And is it actually impactful on the actual output, right? I mean, does it actually matter to do this sort of thing? Or is it just testing because it's the thing you've always tested, right? When you've done the quadcopter board, you've always tilted it back and forth to make sure the motors go. And it's like, okay, well, maybe that's actually not testing anything of use here.
Exactly. So if tilting it back and forth is the only thing you can do, you will do that and you'll sleep well, because that's the only thing you can do. If suddenly you're presented with the universe of opportunities to test things, you're like, oh my God, now I actually have to do it.
Right. I'm going to be here a while. Yeah. And I guess that does come down to, I mean, that's any test engineer understands the scope of testing and coverage and stuff like that. That becomes a big thing, because that directly ties to your efficiency and how many units you can get through. But yeah, for people that are coming in new, I would imagine that's it. Then could become very burdensome.
Yeah, but I'm joking, of course. I mean, it's a good thing to be able to test. And in the usual scenario, right, we have this example of TF Lite and kind of gesture recognition, right?
Mm-hmm. TF Lite is TensorFlow Lite, is that right?
TensorFlow Lite Micro, actually, it's a long name.
Okay.
So the TF Lite team, the micro team inside TF Lite, they want to enable machine learning on the very edge with very small devices like microcontroller level, sub milliwatt, $1 per unit kind of thing. And to do that is very tricky because it's very resource constrained. So you have to really pay attention to what you're doing and test a lot of things. And very often it's not that things are not going to work per se, but you'll run out of memory and then it's not useful anymore because you have to grab a very expensive board to run this. So how do you put this awesome ML capability into a very small footprint? There's a lot of development involved to make that happen, and then clever optimizations you have to do and verify whether your optimizations don't actually break what you're doing. So we have this test scenario for gestures, right? And obviously what you easily think of is, okay, I'm gonna record some gestures that should be recognized, right? Save that data to a file and try to see whether data from those files actually gets recognized as gestured still in simulation. That's the most basic test you can do. And we have an example online how to do that. And it's already great. This is already testing so many things. It's testing whether your drivers work, getting the data from the sensor, tests whether the ML pipeline is correct, and so on and so on. So there is this kind of Pareto thing going on, where after the initial terror of, okay, I have all the opportunities in the world to test, what do I test? You quickly come up with, okay, these are the things I could easily do with Renode that are going to give me a very good indication of whether my thing didn't completely break down. And people will always come to us at conferences and so on and say, oh, but what if? And yeah, there are corner cases that you're not going to be able to test, right? But that's not the point. Currently, people are just not testing things for the most part, and that's the problem.
Right. Yeah, and I think the focus on the repetition, like going back to continuous integration. So I'd imagine that when you're doing these builds and you're building software, and every time you do a commit, you want to do a full test of the system. Right now, that would be super burdensome, right? I know that like maybe I'll do 10 commits, and then finally I'm like, okay, well, I get the software to build. That's great. I'm gonna go try it on the unit now, and I'll do a test and test something specifically and hope it works and keep going from there. But the idea here would be every time I do a commit now, it goes into a pipeline, it does a build, it verifies it builds, it then pushes it down to the device, it pushes the binary that's been compiled to the simulation, and then it also takes in all this data and checks if that works. Is that how that would go?
Absolutely. A very good point. Yeah. So it's not only the fact that it's hard to test, it's also the repeatability. If there's a human factor in the testing, right? I mean, people get bored very easily. So even if something's a 1 minute procedure, which sounds okay, right? Like taking a minute to do something doesn't seem terrible.
Yeah.
But if you're going to do it 1,000 times, you're obviously going to skip the 990 times and just do it 10 times, which is worse. Like you want to do it 1,000 times. A computer can do it 1,000 times.
So I always talk about my own. So one of my like personal faults is like when I get like really frustrated with something and something's not working, I do this thing called thrashing where I'll just change a bunch of stuff, right? So like to give like a really stupid example, I might like say I had like jumpers on a PCB. I might go and change a bunch of jumpers and try it again, change a bunch of jumpers, try it again with like, this firmware that's not working. And then there's no guarantee then when I go and I'm like, oh, I got it working, and then I go and write some more code and I try that, and now are the jumpers in the right spot? I don't know. Like, I mean, I could go and check, but there's a very obvious like point of human error there that could be occurring in that the jumpers aren't set. And it sounds like in this case, using this simulation checks that the jumpers, in this case, virtual jumpers, are always set properly.
Yeah. I really like how you think about Renode, because that's exactly the kind of points that we've always been making. If you go back to 2010, when we more or less started the company, Micro was built with this mindset of we have to make things repeatable and verifiable. Like if you're working with something and it's not working, you shouldn't do what you're doing. You're a human. You're gonna do what you just described, right? I'm not saying that we're not human, but like our approach has always been to
Ant Micro, get rid of all the humans. Got a new T-shirt for you, Michael. There you go.
So the point is, humans make errors, and it's okay. We're computer scientists. We know we make errors. We are trying to figure out ways to be productive, to focus on the stuff that's really creative and get rid of the human errors everywhere. And so what we noticed early on is that when we're working in this physical realm, it's like always what you described. You get something wrong, and then you try to figure it out. You move things around. You change jumpers and things like this. It's unstructured.
I mean, hell, you go out to lunch, right? I mean, you come back after lunch and you're like, what was I even doing? Like, was that supposed to be there? I don't know. Like,
yeah. It's so many vectors, right? So we always say just observe the minimum, change that you possibly can and see whether things improved. And even before we had Renode, and even in places where Renode couldn't be used because, I don't know, we didn't support that platform, we always had this mindset where if you're testing and things are not working, just get back to the simplest possible scenario. Just eliminate any complexity.
Get a Blinky.
And then go one step further. And of course, doing it manually is just frustrating, but it's still worthwhile. We still think it's useful to do it that way. But if you get superpowers with the tools that you're using, suddenly getting back to first principles in a way gets simple, right? It actually gets pleasant and nice and the preferred way to work. And then people start doing it universally.
Yeah.
So I mean, we are focused on working that way even when the right tools don't exist. And in some spaces they don't. Like if you look at the ASIC development, at least today. They don't exist, but you should try to think that way, and then you will eventually create the tools needed because you'll see, okay, that approach is working, and how do I make that approach universal? How do I make it easier to apply in practice? And that's when people realize, okay, I need simulation tools, I need like linters, I need things that help me to do it more effectively.
Yep. Yeah, so I know James Grenning, and he does like tester-driven development, and so I've read some of his stuff on firmware and stuff like that, and it does always seem like in firmware specifically, like where there's hardware in the loop, one of the struggles was always like creating tooling to make these things happen, right? Like, how do you write the tests before? And so it was almost like decoupled from the hardware. It was like, how do you have to write a test and then you have to interact with the firmware, but it's not even thinking about. It's just like thinking about that function instead of thinking about the thing that's out there, the hardware that's out in the field. And so this is basically saying now, like, oh no, the hardware is out in the field. It's just not really hardware. It's like virtual hardware.
Yep. I think that's another right point. We have to make hardware irrelevant in a sense. So all those kind of tool chains that people have, all those like different IDEs, tools, everything. I mean, these are tools of the trade, yes, but ultimately what you want to do is you want to execute code and get stuff done. And all those differences you really want to encapsulate somehow and make it easy to work with hardware. That's what RISC-V is doing, by the way. That's what Chips Alliance is trying to do. We're trying to make hardware almost boring, just like software is boring, right? Like you start a website and you create your React app with this kind of automated scaffolding script, and you don't even know what's going on inside. We like to know, like we're this kind of weird company that loves to dig into everything. So it's not that you shouldn't ever bother and see what's inside, but most of the time you don't need to be looking all the time what's inside. You want this to just work, and the way to get it to work is through tooling.
Right. And I think that probably resonates with people here too. Like most of the time, people like to dig in, of course, into fun problems in hardware and things like that, and sometimes even make low-level hardware designs, like transistor-based designs, things like that. But when you're trying to like get a job done, usually it's more on the application level or like the functional level of like, I just need Wi-Fi to work. I don't care how it works. It's just like I need to make sure when I push a TX packet to it, it sends it to the network. Like that's what needs to happen. That kind of thing. I think that is becoming, just because people are asked to do more with less these days too, it becomes almost a necessity for jobs, just to get things done.
Yep. You mentioned networking here, and I think that's a good thing to focus on too. So we very early on in Renode's development, we realized, okay, getting one device to work is great, but what if you suddenly want to work with a network of devices? And we realized that this is even harder because there is practically no possibility of reproducibility and traceability in such a setup. Like, you have multiple devices communicating, and very seldom will you get them to actually do the exact same thing twice, because they're multiple things. You program them independently most of the time, and they might be different architectures even, or at least they're different boards running different software. So how do you build a network in a testable way? And simulation again becomes the answer, because of course in our tool it's just one virtual setup, it's one time flow that you completely control. All those devices exist in one world. You can position them virtually in different places and see what happens. We have the ability to kind of say, hey, this radio only reaches 10 meters out, and that other device is 11 meters away, so the packet's going to get lost. What happens then? How do you test your protocols? I mean, in practice,
if you're having like 50% loss of your packets, then is your retry working properly? Like, and I can imagine if you're in the real world, you could put some stuff in between the two things and hope for the best, but like getting that exactly 50% packet loss that you might see sometimes in the field, it's like, oh, you might not get that in reality.
Yep, and I think you touched upon a very important thing about testing this kind of stuff as well, where you should actually care about getting a 50% packet loss more than testing whether a wall of the concrete type breaks your system, but the wooden one doesn't, right? I mean, these are on some level important things that people are working with and the researchers are researching, and they should. But in your practical use case, you mostly care about, okay, what happens to my protocol if my signal gets interrupted for whatever reason, right? The reason is not really important. The effect is important. The packet got lost. What happens now? We can simulate that very easy. We can't simulate a wooden wall, right? Like there is no possibility to simulate.
I mean, you could, if you had enough time, you could, right?
Yeah.
I mean, but it's kind of silly.
It's kind of
right?
outside the scope, yeah.
Yeah, right. Yeah, I mean, a lot of this stuff sounds like, I mean, so that specific thing, what that triggered in my mind, I was thinking like, this is what NASA does all the time, right? Because they just have to simulate every single scenario. They have to get every single like, all their retry protocols, all of their RF stuff, every scenario that they expect to see in space. They don't get to send, they don't get to send more than one thing, so they have to simulate it. It's almost like bringing NASA level stuff to the masses. It feels like.
Again, I like your recap very, very much. I hope someone from NASA's listening, right?
I'm your new marketing person. Sorry, you're out of a job. Get the humans out of the loop. Yeah.
We need more marketing people. So if you're listening and you want to do marketing for us, then, yeah, reach out.
That's great. One thing I wanted to ask before we move on from this stuff is what happens if, like, how do you verify that the simulation is actually representing reality, though? Like, how do you validate that piece?
That's one of the tough questions we get asked. And obviously, there are no simple ways to do this other than just verifying with a lot of software. That's basically what's our approach. It's worked for us very well, where ultimately what we care about is running software, right? So if all the software that we know is running as it should, probably the models are good enough. How we create the models is typically based on data sheets, and of course, like data sheets can also contain errors.
No, those have never been wrong. I've never gotten a bad data sheet.
Or we might get something wrong, and it happens from time to time. So and many people say, oh, haha, you have no way to guarantee that these things are correct. Well, yeah, but so what, right? Like
right.
You are effectively trying to improve a very broken reality, and if you get it right 99% of the time, and over time as well, since it's an open source project, things just get better on their own accord. Like people find bugs, yeah, and then they file issues and issue pull requests, and the models get improved. And as we have so many people using Renode now that if all of these people's software works, what's the chance of the models being wrong? It really goes down to almost zero. Having said that, of course, yeah, it would be great to have formal proof and so on. And there's people working on these kind of things as well. It's just that it seems the most practical approach is just to go and get it done and be aware of the fact that yes, the models can be imperfect, but for the most part, you don't really care about them being imperfect because you're testing very specific things. Like if you look at the coverage of software against what hardware enables, very often we see that the software is using like 10% of the hardware's functionalities at most, right? I mean, it's using the CPU very, very much, right? But it's
right.
In terms of the I/O and the registers, and you're just using a very small subset of what's available. So modeling everything and trying to get it perfect might be eons of work where you don't really have the time, right? You want to model as much as needed, as well as you can, and make it available to people, and then improve it iteratively over time.
Yeah, and I think that actually leads me to my next question here, because it seems like, so like looking at your GitHub page, it seems like a lot of the stuff that is on there is kind of these higher end, like you've mentioned, you're targeting AI, ML type stuff, machine learning, artificial intelligence, stuff like that. Do you find that people that are mostly using it are in that kind of high complexity software environment trying to maximize throughput versus, someone like me who's doing like tiny embedded systems trying to, make a, little widget that has sensors connected? Like what would you say the split is in terms of the community?
Oh, I think your use case is great, right? So it should be fairly well split
Sure.
again.
Yeah,
Like
I'm not saying it's a bad use case. I'm just saying like who's really into it. I mean, part of it might also be just the nature of the person using it, right? I imagine someone using like a Jetson Nano is a very smart software person who's like I have no need for that sort of thing, right? And so like I'm not writing a ton of software for it, so the tooling might not have been the testing tooling might not have been a priority versus someone who's doing low level sensor type stuff.
Sure. So disclaimer: we don't simulate a Jetson Nano today, right? Like we do want to do that,
sorry.
but it's a fairly complex thing. But in terms of the complexity, I think it tends to be that people that hit some kind of a complexity problem start thinking, okay, how could I actually test this, right? So currently, I guess that our users would be more like power users that really kind of need Renode, because otherwise they can just get by with like, I'm going to test manually, right? But we do want to reach out to more people, and that's going to happen with this edX course and other things, where we do believe Renode's very useful for a lot of use cases, not just the most complex ones. But I think there's a natural affinity amongst people that are trying to solve complex problems to look for tools that are going to help them to do that. Like RISC-V is a good example where we have a lot of usage in the RISC-V world because like RISC-V is trying to push some boundaries, right? And it's not as easy to program against RISC-V yet because, software's, it is mature, but it's not like ARM level mature yet.
Yeah, right.
There's a lot of stuff out there, but there's still a lot more stuff coming. And so we see all those customers and users in spaces where they're trying to achieve something unique and something, that's pushing the boundaries somewhere. That's when they will turn to new methodologies, new workflows, and they'll potentially run into Renode and start using it. Versus people who have just gotten by doing simpler stuff and it's worked for them. And, I still think they could benefit from using Renode, but I wouldn't necessarily want to like push them to say, you use Renode and your development experience will get 10 times as good. Perhaps it won't, right? Because your thing's just not complicated enough to warrant having to use that additional tool.
Right.
So yeah.
Yeah, there's like some crossover point between like the investment of time and the like the benefit you're going to get out of it. But over time, as someone gets better at it, that investment of time will probably amortize over multiple projects as well.
So having said that, we are currently integrated with the Arduino IDE, right? So
cool.
That'll probably expose us to a lot of people with, that are not necessarily pushing any boundaries. They're just trying to build this Blinky thing, and that's okay too, right? I mean, Renode and this kind of way of thinking should just be universal. We assume that we don't necessarily want to gate it against people that, your use case is too simple, we don't want to enable you, right? No, it's like we want to enable everyone that wants to use it.
And it's enabling a methodology. There's Renode behind it, but it's like this idea of like testing and having, abstracting out hardware basically, which I can imagine, for the amount of people that are coming into the Arduino world from the software world specifically, it probably would actually match up really well. So that's great.
Yep.
So let's talk about the RISC-V stuff. So how does that play in? So people are free to go and use the RISC-V Open ISA and build their own thing, right? Build their own chip. And they often start, they simulate the actual silicon that's happening internal to the chip. How does that tie into the Antmicro ecosystem? Are you enabling that simulation at the transistor level of, a RISC-V design?
Okay, so transistor level simulation and generally speaking HDL simulation, this is of course a bit of a different field that we're also active in, right? So this is not really related to Renode as such.
Sure.
You'd very often use tools like Verilator. Perhaps even more complicated, simulation tools if you're really interested in building the low level phenomenon, the ASIC. But if you're interested in the digital behavior of the ASIC, but you kind of want to test it on a deeper level, that's where you'd use HDL simulation with things like Verilator. There's also proprietary tools that people use for that, but like that's where we think Verilator and what perhaps comes after that is the way. You want it to be open source. You want it to be available to anyone, even if it's complex stuff. You want as many people as you can looking at the problem and joining forces to develop, open source silicon. So we're putting a lot of weight and development effort into things like Verilator, which is enabling people to work with, hardware software co-development. And I mean, Renode's enabling that too, because people use it for that kind of stuff. But of course, Renode's more into behavioral simulation for software development, right? If you're interested in the hardware as such, you might also combine Renode with Verilator. We have that capability to co-simulate parts where part of the system is fixed and known, and then you simulate that in Renode, but then there's a peripheral or DMA or whatever that you simulate in your HDL simulator, and you're looking whether your development is going the right way, and most of the system is simulating very fast, and that part that you care about is simulated slower, but since it's just a part, the overall result is pretty good. So we have that capability. And of course, there's other tools in that space. Sci-Fi in Berkeley, they're doing a great job with Fire Sim. That's like a simulator for chisel-based designs that you can run in the cloud, and you simulate the entire chip at the same time. So yeah, it's a fascinating area as well that we also want to revolutionize. So we want to tell people, hey, this is all possible using open source tools. And once you get to open source tools, you can have workflows that you can put in CI, make available to everyone, show it to the world, and collaborate around.
Yeah, I imagine so. Tim was back on here talking about Tim Ansel was back on here talking about the open source PDK, and we're very excited about that. One thing that always comes up whenever I think about like the idea of making a chip, it's like, okay, well, first off, where the hell do I start? That's obvious. But then, when you think about that application level thing, like first off, why do people want to do this? I actually really like that example you gave of like, so now you have captured data of someone like waving their arms or like a gesture, and you're trying to make that better. And right now, what the OpenML people or not the OpenML, but the Lite TF Lite. The TF Lite thing is basically writing software to like push that onto a fixed piece of silicon that's out there, low cost fixed piece of silicon. What I'm imagining the Verilator and this kind of co-hardware software thing would be is now you have someone waving their arms, you have that captured as a data file. Now you have the system the system simulated as well at the behavioral level, but you might then go and try and make a custom piece of silicon that really, really efficiently could capture and process what that data is. Is that kind of the thought there? Is that what you're thinking is happening, or how does the actual?
Yeah, we'd always wanted to close that feedback loop where silicon manufacturers, they think they know what software people need, and that's not true. They don't.
Okay.
They're getting better and they're hiring some clever people, but ultimately it's the software people that know what they want. And very often, like so many times in our history, we'd bought a piece of silicon and then just felt very sorry that it's not doing exactly what we want. Like you just
Can you give
compromise.
an example of that? Like what was the actual compromise on that didn't fit your need?
Very often it's just one missing interface. Like if only it had this one extra interface here, that would be applicable to just those awesome scenarios. But as it stands, like you have to add more chips and complexity and software. Like you effectively patch up the whatever the hardware is missing, and you never get back to the silicon vendor and tell them that, right?
Yeah. Right. Yeah, it's like, hey, ST, you gave me 5 UARTs and I needed 6, and that last UART really mattered, like that kind of thing, right?
Yeah. You never get that. Like, they try to get that feedback from you, but like there is no way you're going to give them that feedback easily. So, in fact, we're still very often, they do talk to some people, right? They just talk to a subset of people.
Sure. Yeah. And usually the ones that are paying the most. I mean, because it's like a power distribution pretty much.
And these are the people that are paying the most today, right? These are not the people with the potential use cases. So it's a chicken and egg problem that you're facing. So I think FPGAs solve a part of that problem. And we think that FPGAs will become, much more used than earlier, where you need some flexible hardware. You need to kind of adapt your platform as time passes to specific machine learning use cases. FPGAs are a great answer because you can just change whatever's running inside of them, adapting to your use case over time. You don't have to like tape out a new chip. You just kind of push a new bit stream onto it. So in that sense, FPGAs solve a part of this problem. But if you really want to go down and optimize a chip to a very deep level based on your use case, that's exactly where simulation comes into play. That's exactly where open source PDKs come into play. If we democratize this ability to build chips, people will finally have the ability to not be afraid of thinking that way. Because right now, if you thought, okay, my hand waving will influence chip making, it's ridiculous, right? It feels ridiculous to be making that statement. But in fact, it should be like a researcher, kind of takes a specific thing into question, right? He says, okay, we should be able to devise a very good algorithm to detect gestures, but the current hardware does not support that very well. So what? I can create my own hardware. I can kind of look at what's needed on the hardware level, like model, implement that, kind of simulate that first, like test this approach. And if that approach seems to work, if I'm getting much better performance for this specific use case, let me go and just get my chip made that does this. This is possible. This is going to happen in some years, sure, but there is no reason why this shouldn't be possible. We have people in the security domain that prototype stuff in Renode first. They see whether this has any, like, effectively what they're modeling is performance, right? Because they're trying to, it's Dover Microsystems, a company doing, security chips that kind of guard, they call it core guard, right? It guards your, code from executing malicious stuff, or your CPU from executing malicious code. And they're looking at various ways to protect this. So they're gonna experiment with various like guards they can put in place, policies they call them. And of course, the best policies would be the most stringent ones, but very stringent policies result in a huge performance decrease.
Right,
So these guys have been working with NXP and putting that IP into their next gen platform, where they have been using Renode to see which approaches work best and kind of cut away the approaches that just don't make sense from a performance perspective and focus on whatever matters, like whatever gives them a good Pareto optimization of this gives me a lot of security, but at the same time it doesn't give me a huge performance decrease. And then after they've done modeling in Renode, they're going to go and implement the actual hardware code that eventually gets taped out in a chip. So that's how we want people to work, right? So FPGAs are one way, of course, because they're awesome. You can just change them in runtime, but ultimately you'll also be able to kind of build chips that cater for a specific use case.
Yeah, I think that is the workflow of the past, but also the future of have an idea, try it on an FPGA, optimize, and then eventually move towards like a custom chip solution. I think maybe what happens with some of the chip solution or the open PDK and more fabs hopefully opening up is like it just gets faster and easier. That people are like, oh well, I'm not going to do another rev in FPGA. I'm just going to go straight to a chip. That kind of thing would in a near term future I could see that happening, where democratization of chip shuttle runs could be really, really beneficial in that way.
Yep.
So Antmicro is listed on the microchip, and you guys are site, and you guys are working with the Polar Fire. How do you actually interface with an FPGA? Like, so what tools then do you hook into, and how does that interact with some of the other tooling that you've built up?
So of course, Verilator is the default thing that we talk about there, because it allows you to just grab your FPGA code, put it through Verilog, and then hook it up to Renode and get it co-simulated. When it comes to like FPGA stuff that we work with, like for example Litex, which is a configurable system on chip generator that you can run inside an FPGA. You can have some RISC-V cores, or if you don't need cores, you can also have just different kinds of I/O peripherals. So Renode, for example, gives you the ability to extract that Litex configuration and generate this platform definition file based on that, right? So we're looking at specific FPGA IPs ecosystems that are in a way fixed, right? Like, sure, you can change them because that's what FPGAs are. You can completely change everything that goes on inside them, but we try to kind of identify places where we could possibly simulate those things in a consistent way, in a configurable way. But the configuration is not like you don't have to hand code that configuration. You can just read it out and build that system easily in Renode. Yeah, and then there's a bunch of things, of course, that we're doing on FPGA front that today doesn't connect to Renode, because we've been talking about Renode all the time, but
yeah, there's more to Antmicro.
It's a part of what we do.
They're taking out humans in more ways than one, folks. Sorry, I'll stop doing that. That's my last time, I promise. Probably my last time.
I'm just laughing because if I confirmed what you just said, I'd be in trouble. But yeah,
I'll just keep saying it, and you can just nod your head silently, as all of our audience member will. Okay.
Yeah, and it's a podcast, so people can't see. Great. So
that's right. Yeah.
So the point is, we're doing a lot of stuff in FPGA space, and like open source FPGA toolchains, right? We're working with QuickLogic, building their current and next gen FPGA platforms where they will have completely open source tooling. Even better, one of the things that we're doing for Skywater PDK Shadowrun, which by the way is closing, and like the first window is closing this week, basically.
Get your stuff in now, folks. Yeah, I think it's 1st of December or something like that. I think it was early December, I thought, or maybe
end of November, actually. Yeah.
Okay.
At 30th, I think. So.
Oh, you know what? Probably by the time the show goes out, this isn't going out, unfortunately, until until the 29th. So if you're listening to this right now and it's Monday morning, get simulating, folks.
So one of the shuttle runs there will be one with Open FPGA fabric in it, right? Like not just Open FPGA as in like something you can target with open source tooling, which is cool enough. It is actually open source FPGA fabric that gives you the ability to potentially build your own FPGA, right? And that's the kind of thing that we're trying to enable. And of course, ultimately, it still plugs back into Renode in some sense, because once you make things easy to work with, configurable, somehow you end up doing simulation at some level, right? Because you want to, like, even if you tape out a new chip and you're kind of completely focused on chip making, I think that's the claim I've been making since the very beginning. Software people should get to say what their chips do, right? So the development perspective, the application perspective, the user perspective should be on your mind, even if you're deep in the lab developing the next gen chip. So ultimately, many of the roads connect back to Renode anyway, but like I don't want to make it sound like you want to develop a chip here, Renode does this, right? It's going to be part of your workflow, but of course, many of the things that need to happen for those workflows to be improved are completely other tools. Like we're working with system Verilog support and Verilator. We're working with OpenFPGA tooling. We're working with like open source ASIC flows and the PDK. There's so many building blocks that need to come into place for this to really change. But it's happening right now, right? Like there is so much development that I think it's beyond the point where it can be stopped. So people can complain that it's taking away their business, or they might be, I don't know, afraid of this new world that's going to happen when these things get open sourced. But I think it's already inevitable. It's more like you can try to stop it and make it go slower, yes, but slower is still happening.
Yeah, just lean in, folks. I mean, like I think you're right. It does change. It changes the nature of like profit streams and stuff like that. And I think that's usually where people kind of clam up, especially like executives and things like that. And I just try and like whenever that happens, I don't try because I know no one in that position would ever listen to me. But what I usually do in my head is like I point to like Microsoft. I mean, look at Microsoft and like their shift towards open source. It's just been, I mean, it's been mind-boggling, and like how successful they've been in the face of that, and just how they've been changing their company culture. I mean, like Satya is just the CEO has been instrumental in that from the top and stuff like that. But it's amazing to see companies that were so closed move towards open and still thrive in very, very big number of ways. It's crazy.
Yeah, it's crazy, but I would actually dare Microsoft to kind of go to the next level.
Yeah, well, of course. Yeah, there's always more. Yeah.
Right. I mean, yes, they've embraced open source very, very much, but like look at GitHub, look even VS Code, right? The nicest stuff about VS Code, like the remote collaboration features and so on, all closed, right? Like the basic tool is open, but the nice stuff is closed. Or GitHub, right? Yeah, it hosts a lot of open source code, but it's a closed proprietary framework, right? And I'm not militant. I mean, I understand why they do it. I'm not going to complain, but it's more like,
don't worry, Stallman's not listening.
Yeah, things are getting better, but they're far from ideal. There's still a lot of work to be done.
Sure. I'm just saying that even like they were known for rejecting it outright in the past, and that's the only thing I'm saying. And like the shift towards it is the right move, I think. So
absolutely. I mean, we are using a lot of their technologies, so I'm never going to complain about their shift to open source. I think it's great, and I think they did the completely right thing. But what I'm saying is we shouldn't just stop there, and we shouldn't say, okay, now our work is that even Microsoft is doing open source now, so our work is done.
Right. No. Oh, I see. Yeah, right. Got it. Okay. And you guys have an open source section on your website about projects. You list Axiom, Migrant, RISC-V, Zephyr, and ECOS.
That's getting a rework. So like it's this list is so incomplete. It's coming from like many years ago. And we're working on a new open source portal where we're going to be listing hundreds of the projects that we're participating in, not just a bunch. And the bunch there is just probably a little bit old stuff like Renode, of course, is still there and growing. And Axiom is a 4K camera project that we were involved at one point, and it's an awesome project that's still living on. So I'm not saying that it's kind of dead, but it's more like our participation in it is not as active as it used to be.
Got it.
But there's like dozens or perhaps hundreds of new projects that we've since either started or got involved with, and the open source portal will summarize that much more neatly. So sorry if you hit that open source button on our page, and I promise to kind of make that better. Certainly you should go to our GitHub and just see about the number of contributions in various projects. And
so how do you decide on like so obviously you're paying engineers to do all this stuff, and how do you decide what to get involved in? I imagine, like we were just talking about with a Microsoft, there's probably not a profit mode in all of this, and like you and I talked about before the show, you are very mission driven as well. So in a world where you can work on everything, bring this kind of methodology to everything, how do you decide what to work on next, and then what ends up impacting your business as well? I mean, I guess.
We mostly decide based on actual impact factor, in a sense. Like we look for things that are really broken and try to fix them. And then if you try to fix them and you just let go of the fact that you're looking for immediate profit, right? You're not looking for immediate profit, you're looking for profit further down the line. And so what's going to bring people money? Fixing problems, right? So you want to fix people's problems so that they feel inclined to pay you for having fixed them. And we're looking for areas where open source is not really very popular, and we think it should be. And we build like open source baseboards, we build frameworks, we build tools wherever we see a need for them. So we're probably not going to build the next generation like a front-end framework, right? Just because that space is already very crowded, and we might, right? We're crazy. We might actually go and build the next gen, front-end framework too. But probably look for us in spaces like hardware, like ASIC design, like FPGAs, where there's such a dire need for revolution, where we're just going to identify what needs to be done and try to do it. And obviously we look for partners, we look for customers. So wherever there's customers like Google, Western Digital, and others that are working with us and willing to pay for developing open source, we're going to go there and do that, right? Because that gives us a sustainable model to actually continue doing that over a longer period of time. But very often our will to get involved with something predates any profit, right? We just see this is really broken. Let's just try to get involved, and obviously over time we're going to find a way to monetize that, and it always happens. So
sure, yeah. I mean, yeah. I'm always surprised by people that they give their time to a project, and then that project goes somewhere, or someone is looking to utilize that work that's been put out in the world, and it's like. It's either midstream, or it's, at the beginning of the stream. And it's like, at some point, someone's going to say, oh, I just need this to work right now. I'm willing to pay this person to go make it work. So yeah, I could see that being it's almost like a marketing in itself of like, hey, we're doing this thing because we believe in it. But also, hey, look, all these services we provide, we can just do this more, you got to pay us to focus on one thing. So you guys are, like you said, you're a services org first. You provide services, things like that. Renode is a project that has come out of this and become this thing that you use. But then you'd mentioned like an online like a CI like tool, or like tooling. Is there like a web tooling kind of thing that uses this, or is it more like you pay someone at Antmicro to go and build up the tooling for an organization?
So, of course, we have organizations that don't want to share anything that they do, and they just want to use open source tools internally, and they have confidentiality reasons to do so, and
Sure.
they're users, right? And they pay us to develop something just for them. But we love when, of course, people are working on an open source project, but that's driven by a corporation. And the TF Lite guys is a good example, right? It's a Google project that is being done in the open. And for them, we're building a completely open source infrastructure for CI that is out there for everyone to see. So we have the ability to build those kind of things. We're using things like GitLab and BuildBuddy and all sorts of frameworks that allow you to run CI, present results, analyze them, and so on. so we have both, right? We have customers that just want to do something specifically for them, and that improves the core frameworks that we work with. That gives us revenue streams. That kind of it's a very important part of what we do, and we don't want to like discourage people from working with us because their stuff is closed. It's more like we can understand how it's not a switch you just flip and suddenly you just release everything you do open source.
Right. Try one small thing that might be open and see if that goes in the future. But if not, that's okay. There's business cases to be closed sometimes too. Yeah.
Effectively, of course, we do believe that we're going to advocate our customers to try to open source as much as they can, right? So it's just that it's a step-by-step process. You don't go to a big corporation and tell, like, who do you tell that? Like, you don't go to the CEO to talk to him. You're going to be talking to some kind of a team that's very convinced they should be doing open source. But before they actually get the buy-in internally to do more open source and to influence their organization, it's going to take time. So we're fine with like implementing a system that's working internally for that company. And over time, since that system uses open source tools, you can convince them, hey, what if we did a public CI? Would your world collapse if that happened? And very often the answer is, okay, well, perhaps it's something we could do.
Yeah. It's like if you're going to hire Antmicro, don't expect to be sitting in a conference room and don't be surprised if they suggest something might be open at some point. That conversation is going to happen.
It is. Yeah.
Yeah. That's great though. I mean, I think that's, you guys wear that on your sleeve and people know about that, and it's if they're surprised, they just haven't done enough. They haven't done enough research. So where do you see all this going? I mean, what's next in the wide swath of things that are out there? What are you most excited about in terms of all of the things that you guys are working on that is open?
Well, in terms of the things we're working with today, I'm of course excited about the FPGA stuff because it's really taking shape and gaining momentum. The ASIC things, the PDK and so on also are, and I'm very excited for them. But it'll take a much bigger coalition of players to make it happen. Hence, Chips Alliance, hence RISC-V, and so on. But yeah, I'm super excited for that too. I'm also excited for the things that we're, like looking at and we know we're going to get involved with and things that other people are working with. Open source self-driving from ComAI or like medical research that kind of advancing this possibility that humans will eventually try to fight the results of aging, right? I feel there's a huge field for open source to play a role in everything, and I'm very excited for the fact that we don't have those limits. And Micro's never going to say, hey, this is the kind of stuff we don't work with. I mean, unless of course there's a problem with the stuff. But I mean, for fields of human activity, for fields of research, if there's innovation to be brought into those fields using open source, we're up for it. It's easy to do in hardware, FPGAs, ASICs, in the sense that you can see the clear connection between software and those things, and then you can just rely on existing examples and just telling people, hey, look, it's worked for software, why shouldn't it work for hardware? But it's worked for software, why shouldn't it work for biology is like a perfectly fine argument I'm willing to hold in front of anybody. or smart home or whatever. We were kind of looking at ways.
I'd say biology and smart home are very, very different.
I know. I'm just, that's why I'm throwing these things out there, because it's not very structured. It's much easier to structure your argument in specifically, semiconductors, software. These are so well related that everyone sees the connection, and it's hard to argue. But I'm willing to claim, like, open source design has always been on my mind. It's been inspiring me. Like, how would you go about kind of helping designers be more productive with open source? I'm sure you could, and today it's a very proprietary landscape, right? But I don't see a reason why it should be so in 10 years. It's just that we're not tackling this problem right now because you just have to target what's feasible today.
Yeah. Right. One foot in front of the other.
But I'd love to, right? Like, why would someone say that the current situation is preferable to having something that's collaborative and people just, working together on improving the tools and not just using them? I'd love to have a community, not even a community, a society of tinkerers rather than a society of consumers and users of technology.
Yeah. That's a great lead in. So, what is it? I don't think we've talked about the Chips Alliance yet. What is the Chips Alliance?
This is an organization that tries to drive open source hardware development in a very broad sense of the word, both like IPs, both things that you make, but also how you make them, the tools. So there's those two pillars where, on the one hand, it's what people traditionally think about when they think open source hardware, right? Like open source cores, open source interconnects, open source I/O peripherals. That's all within Chips Alliance's interest. But the second pillar of tools, I think, is really cool because Chips Alliance also thinks, okay, if these things are going to be built in an open way, you also need them to be built in an open way, like in terms of tooling and workflows. You want people to be able to collaborate around these. So you don't want an open source IP core that then nobody can use because they can't pay $500,000 license to work with it. You want people to actually be able to take that from GitHub and then run it on their own computer or perhaps in the cloud and proceed to eventually perhaps even making a chip based on that. And of course that needs some money and infrastructure, but like today building chips just needs a ridiculous amount of resources, way too much resources compared to what it could be. So it's bringing out the barriers in all sense of the word, both giving you like off the shelf stuff that just works, that's like one aspect, but also changing workflows so that anyone can get started easily.
And so, what does what does it take the form of? I mean, is this like a working group, and it's like there's kind of recommendations that are made, or you discuss this stuff? What is the actual output of the Chips Alliance?
So it's a Linux Foundation project that gets involved both with code and specs. And traditionally, let's take a project from Intel called AIB. Intel's a member, right? And they have this interconnect project where they develop the spec and the code alongside. And I think that's the best type of thing to do, where you both have an open spec that other people can try to implement if they want, but you have a reference implementation. And I think Chips Alliance is really great for doing this, where it's not just a spec body where we just come up with complicated specs and then hope that other people will understand what we mean. And it's also not just like an implementation, but we just do stuff we don't know what we're doing, right? It's both. And of course, not all of the projects in Chips Alliance have a spec, right? Because sometimes you're just building a useful tool that doesn't really need a formal specification for 20 parties to adhere to. But things like interconnects, right? They do need specs.
Yeah, right. Yeah, pin one has to hook up to pin one. You know, like you can't just be well, whatever you feel like.
Yeah. So I think this combination of the tooling aspect of an IP aspect and then specs and code, I think covering all of these things, this is super ambitious, right? This is something that
It
we're
is a lot.
really trying to pull off that's not trivial. But at the same time, I think that's what makes Chips Alliance worthwhile because there are plenty of organizations that tackle much less complex problems. And RISC-V is one example. It's developing an ISA. It's still very hard to do that, and like the ISA is not the only thing. You need also an ecosystem around the ISA to make it work. And I can see RISC-V currently expanding to cover so many more fields than it used to. And part of this is because RISC-V has realized, okay, we now need to be much broader to make RISC-V go to the next level. Right now, it's already super popular. There's a lot of companies and universities working with RISC-V. There's products. There's a lot of momentum. But to make RISC-V really omnipresent, you just need to take care of the entire ecosystem, not just like the ISA and that's it. Similar
Yeah,
Chips
right.
Alliance, right? If you want to make open hardware successful, you can't just say, oh, the cores are successful, mission done, complete, right? You need
Right.
to think about how are people going to connect memories to my chip? How are people going to do AI acceleration? How are people going to do graphics? You know, there's so many complex problems in one. But I think that tackling this problem also on a methodological level will allow us to scale very rapidly once we're past some inflection point. So it's still pretty early in the game, but I think that focusing the tools will help us also like bring together the people that care about these things, and they will bring, like we already see organizations like Intel, they joined bringing in the AIB stuff, and you know they were looking for a good place for it to live, and they found us, and we're looking for these people that have this jewel that are sitting on and thinking, how will I make that a sustainable piece of silicon, this piece of IP? And they look at the landscape and see Chips Alliance as this potential body that will make your thing successful and make it interoperable with other things and make your development workflow better all at the same time.
Yeah. It's interesting contrast actually to our guest last week. So last week, Joris had worked at Tesla, and we were talking about a vertical integration and like how vertical integration basically removes some of the need for this sort of like the need to communicate between organizations, the less need for standard, less need for just specifications on different. Obviously, you're going to have that internally, but it's not going to be as much rigor around it because you might want to move faster. Do you find that this makes things move slower, or what do you find is the ultimate benefit? Is it the interoperability that becomes the benefit?
Well, I think vertical integration shouldn't be contrasted with what open source does. I mean, essentially at
Okay.
Micro,
Yeah.
because of using open source technology, we can have infinite amount of vertical integration, right? Like we do a lot of
Mm-hmm.
our own tools and frameworks because we are using
Mm-hmm.
open source, so we can just integrate them together. Now, as a side effect, we also open source a lot of these changes, and the reason is if we get more people hooked on this, they're also going to contribute. They're also going to verify,
Yeah.
validate our use
Yeah.
cases. So I'm not seeing how these things are in contrast. I mean, sure, vertical integration like makes your life easier in some sense, but like combining vertical integration with open source, I think gives you the ultimate benefit.
Oh, totally. Yeah, I'm not saying. Yeah, I'm not saying it's not good or bad. I'm just saying it seemed different. It's a good point about maybe it's not. They're not mutually exclusive. I guess the main thing that I think about is one thing we talked about was like the scale required to be truly vertically integrated because at that point you basically become the standard, right? You're big enough that like other people come in again. Just to use the Tesla example. It's like, oh well, this is our plug interface, and you just got to follow this plug because that's what we say it is. And in this, it's contrasted to this it's a bunch of people saying, well, what is the plug actually going to be and what is the best case for the plug? I think the benefit would be if you have a bunch of people looking at it before it's finalized, it's like, oh, well, why is it doing this? Let's actually change this and make it a little bit more useful to more people. So that actually could have one of the main benefits, I would think.
Yep. And I think that you make a valid point with the scale thing. So what open source enables is achieving that kind of thing without scale
Mm-hmm.
in a sense. And
Yeah,
then
right.
once you
Yep,
get the
yep,
scale, sure, you can set your own standards. But by that time, I
yep.
don't think you actually want to. I think like if you become big on open source, which is what we're planning to do, you'll realize that yes, you're hiring a bunch of smart people and you consider yourself a smart person, but that doesn't mean that you've just devoured all the knowledge of the world, right?
Right. It's
The
not the
collaborate.
answer.
So the collaboration perspective, the ability to collaborate that open source gives you, I think just improves your like vertical integration
Yeah.
experience because you can just borrow ideas and code
Yeah, right.
from other places and integrate that back into your stack. And the way you
Right.
put these things together, the way you make these things work, that might still be unique to you, right? So we're not open sourcing all of Micro and like our entire internal infrastructure and the way we do things and so on, right? We're open sourcing code that we work with. We're open sourcing tools. We're telling people how we work, yes, but you can't really copy what we do so easily. So in that sense, a company that wants to be vertically integrated and have some competitive advantage over others while being open source at the same time, they can still perfectly do that, right? They can open source all the building blocks, but the way they put them together, the company culture, all of those things,
Mm-hmm.
it's I think unique to an entity, and it's very hard to just like copy that one to one. You can try, but like there's been many people that have tried to copy organizations and of course failed to do so. So I don't think code is equivalent to everything that a company does. So I still think a company that builds on top of open source can be vertically integrated and kind of protect their spirit in a sense, but at the same
Yeah.
time be very open about the technologies it uses and collaborative around the code that they develop.
Yeah. No, I think you're right. I think you're right. And I think the culture is a big piece, like you're saying. Michael, where can people find out more about Ant Micro? And I think actually probably most relevant for this audience, how do people get started with Renode quickly?
Okay, so about Micro, I think you just go to antmicro.com and there's a technology showcase. Like if you scroll down, there's like a bunch of tiles with different blog notes that you can read about the
Mm-hmm.
things we do. That's where I mostly point people to. The open source portal, once created, that's where I want you to go as well, but it's not there. For Renode, just go to renode.io. Or you can just open the docs for it, and actually go to GitHub/Renode/Renode, and there in the README, there's installation instructions. If you're on Linux, it's going to be very easy for you because you can download a tar file that contains the so-called Renode Portable. And Renode Portable is, I think, a 20 meg package that you just unpack, and there you go. You run Renode, no dependencies.
Yeah, I actually clicked it before, and it was, I think, like 8 megabytes, and it was like a Debian file that just like you just click and.
Oh yeah, you've already got the deb file, right? But I mean, there's also a portable file where you don't have any dependencies whatsoever, because the operating system packages, they'll of course have some like dependencies, not anything dire, but you'll have to do a little bit of configuration. But the portable package, it comes with everything prepackaged, and it's a really good starting point because people want to see an effect in 5 seconons, and I understand. I'm the same. I see a new framework, like, how do I try it out in 5 seconds? I don't have more time.
Right. I'm going to spend the next 3 months on this thing, but I better get that 5-second dopamine hit, or else.
So look at using the Linux portable release, and if you follow those instructions, you're going to get going in 5 minutes, and then we ship with examples. So if you go to our documentation and you look at the supported boards, you're going to see like a bunch of boards, and for those boards, there's a single command to run a demo running on those boards.
Oh, that's cool.
Yeah, and you get a binary running, you get some console, like you're going to get UART output in Windows, you're going to get a log of everything that's happening, and you're going to get an interactive terminal for your kind of interactive work. So once you turn Renode on, you're going to see the terminal, that this kind of monitor, as we call it, this interactive terminal. And then if you just enter that one command that runs the demo, you're going to see things happening. You're going to see, like UART spitting out things and the logs saying, hey, we're accessing peripheral XYZ. So that's what you should expect.
Yeah, that's cool. All right, great. We'll put links into that, to everything here. But Michael, thank you so much for joining us here. You mentioned you're looking for marketing people. What other kind of people are you looking for?
Enthusiastic about open source, and people that can actually understand the premise of what we're doing and why. And we're always, in general, not just in marketing, in all the roles, we're looking for people that want to stay around for a while and kind of understand that we're there not to just do some work, but we're there to change the world in good ways. So it's very hard to kind of pin down exactly the kind of people we're looking for. It's people that are excited, of course, like technically competent is important for us as well. But I think that very often you see, people that are, theoretically they're technically competent, and in practice they're like stuck in their ways, and it's hard to get through to them with this message. And then we find it hard to work with them. Whereas if there's people that are enthusiastic, and they might even be, need to learn some things while they're working for us because they didn't know them before, it's much easier to build on that enthusiasm and this capability for learning than it is to teach people that just don't expose that capability for learning. So it's very much about the personality as well, not just about like a specific skill set. Sure, like hackers and people that love to tinker with things and take them apart and like go step by step into figuring out how things work, that kind of mindset is very, very useful for working at Micro. And if you combine that with this kind of affinity for learning and a certain type of personality, and I don't mean we don't want to say that we want to attract people that want to fight against the world, right? We're not really fighting against things.
Right. No, not zealots, you're saying, but you're saying people that are passionate.
We're building things, right? We're helping to create things that are just better than what's existed before. We have respect for what's existed before. You can do a lot of things using proprietary technology. That's awesome, right? Like you can fly to the moon and you can build self-driving cars in a closed way and in an open way. And we're not saying one is necessarily always better than the other, but we're just saying the open way is our way. If you believe in this, if you want to work on those kind of things, come and work for us. And if you don't, then it's fine. Like you don't really need to work for us. That's also okay. You might work with us at some point as well.
Right, exactly. Work with the projects, the many projects you're starting or working on. Yeah, that's great. All right, well, Michael, thank you so much. This has been really interesting, and I'm really excited to try out Renode. So thanks for that.
Okay, fantastic. Thanks a lot. Have a good day. Bye-bye.
Today's episode was brought to you by the raw, uncut, unsimulated generosity of our patrons. Join the club at patreon.com/the Amp Hour, and you'll feel the real-world implications of sponsoring us, like discounts on the atoms of an Amp Hour hoodie or t-shirt. A special thanks today to our corporate sponsor, Bino.